All right, hello. Is my mic on? Yeah? Sort of? Question mark? Oh no. Oh. Well, it looks like the battery on this is dead. Let me see if I can get other batteries. All right, what about now? I'm on now, right? Okay, cool. Welcome to Data 8, Lecture 32. Today we're going to be talking about least squares, and then in the second half of today's class, we'll be talking about residuals. So homework 6 is due tonight at midnight. Homework 7 was released yesterday and will be due on Tuesday at midnight. But other than that, no other announcements. Any questions about that? Cool. So let me quickly recap what we covered yesterday on linear regression. So what we saw yesterday is that if you take some points, convert them to standard units, you can find R, the correlation coefficient, by taking the xy points in standard units, multiplying the x and y values together, and looking at the average of the x and y values. Okay? So if you find the average of that, you find R, which is a correlation coefficient. And what we also found yesterday is that if you happen to be in standard units, the best fit line, the regression line, is just y equals r times x. Okay, so I got a question yesterday which is really good, which was, I thought we said that r doesn't change when I flip x and y, right? So we saw yesterday that the correlation doesn't change when I flip x and y. But according to this equation, if I want to predict x given y, I would move r to the other side, and that would like result in a different value of r, right? Something weird is going on here. And the reason why that happens is because these are not like x and y. This is not a normal, typical x and y like function values. What I'm saying here is that given a value of x, I'm going to predict a value of y. So it's not the same as saying like y is equal to x. I'm saying like given a value of x, I'm predicting y. So if I were to flip my axes here, what I would be saying then is given a value of y, how would I predict x? And if I'm asking that question, then the r doesn't change and the equation still holds. So the slope of the line when you flip the x and y axis is the same. And that's because we're doing predictions. We're not like saying r times x is always equal to y. Now I want to clear that up. So we have this in standard units. So y is equal to r times x in standard units, a very nice equation. And we also saw at the end of class yesterday that in standard units, I can always convert back to regular units. The way I do that is I notice that x in standard units is original value of x minus the mean divided by standard deviation of x. Original value of y is, y in standard units is original value of y minus the mean of y divided by standard deviation of y. And so if you plug those back into the equation and do some algebra, you can eventually get back y in original units based on x in original units. The way we do that is this. So here is the same equation, so don't get scared here. This is just y in standard units, x in standard units. And since we know, if we know the average of x, the average of y, the standard deviation of x, the standard deviation of y, then we can find the original value of x given the original value of y. This is also a linear equation. So here we have a line. When we convert back to original units, we also have a line. Here's y, here's x. We can do some algebraic manipulation here and get back something that looks like y, a familiar equation for the line, which is y is equal to the slope times x plus intercept. So if you do that algebraic manipulation and then multiply out this side, this to over here, and then like move some stuff around, you'll eventually find the slope of this line is r times the standard deviation of y over the standard deviation of x. The intercept is the average of y minus the slope times the average of x. This is just based on algebraic manipulation. What you should really remember here is the original equation. So you should remember this. This is important. And know that if you just plug back in the equations for standard units, you get back everything else. Any questions about that? So if you have some time, I suggest you go ahead and like do this, move stuff around, and actually get back this, okay, slope should be equal to r times this, the intercept should be equal to that thing. And you'll notice from these equations that if x and y are already in standard units, or if they happen to have like mean of 0 and a standard deviation of 1, the slope becomes r times 1 over 1, which is just r. The intercept becomes the average of y, which is 0, minus the slope times the average of x, which is also 0, if x and y happen to be like both mean and 0, both have standard deviation of 1. And you notice that you get back the original y is equal to r times x. So here we're just adjusting for the fact that x and y might not have been in standard units originally. Okay. So go ahead and try this out on your own time, or try it out now. So a course has a midterm, which had an average of 70, standard deviation of 10, and a really hard final. The average was 50, the standard deviation was 12. If we plot the scores on a scatter diagram for the students in the class, and we find that the correlation is 0.75, and we notice that it's a typical, the scatter plot points are in an oval shape, which suggests a linear relationship, so it is a linear relationship here. Then, what do I expect the average final score would be for students who scored 90 on the midterm and 60 on the midterm? Try that with your partner.
What is 90 in standard units?
So you can start with y is equal to r times x in standard units. Then see if you can like work out the algebra to get back the predictions. Go ahead.
The y would be the y would be 1.5 standard units for final exam. Let's try to convert that back to the original unit. So 1.5 times 12. What is that supposed to be? I know 15 times 12 is 100. Don't bother doing it. I know 15 times 12. I know this 180, so it would be 18 plus 50, 68 on the final. Well, dear, I'm really good at more. I'm pretty sure it's a really hard final. 60 minus 70, that's negative 1, right? So that means on the y standard is negative 0.75. I would multiply that by 12. That is 900, so 90 minus or plus or minus. No, it's only 9. 9 plus 50. So 9 on the final. Not really. Wait, am I sure? Yeah. Yeah, but we want to do it. So you have to like I think I'm certain about it. Are you guys curious to do math without calculators? Or when do you guys use calculators?
Okay, so how do we do this? So always, when you're working out these prediction problems, I suggest starting out with just y equals r times x, both in standard units. That is definitely the easiest thing to remember. And if you remember how to convert back and forth from standard units to original units, then you don't really have to remember like really long formulas and all of that. You can just work out what it is originally. So we know that y equals r times x in standard units. And what we want then is x in standard units. So here we have predict the final score for someone who got 90 on the midterm. So the final score is my prediction, y. And what I observe is a 90 on the midterm, that's my x. Okay. So I take that 90 on the midterm. I want to convert that to standard units because I want to go back to my simple equation. So 90 on the midterm, converted to standard units is 90 minus 70, which is 20, divided by 10, which is 2. So here, this 90 is 2 standard deviations above 70. So that means my x in standard units is 2. Y equals r times x. So 2 times 0.75 comes out to 1.5. So my y in standard units is 1.5 standard deviations above y's mean. So 1.5 in y converted back to original units in y gives us, so we have 50, add 1.5 standard deviations plus 18, so we get an average. We predict that this person will get a 68 on the final. So we're just doing some conversions back and forth, doing some algebra. So this one we get 68. If you get 60 on the midterm, the process is pretty much the same. So convert to standard units, the midterm was 70, the midterm average was 70, so this was -1 in standard units. Multiplied by r, the correlation. So we get back one standard deviation below, multiplied by 0.75 is -0.75. Then we can do the same deal. And I'm just going to show you how that works. So I have, okay, go. So here we go. Make that bigger. Here is discussion. So we had here, midterm was average 70. So midterm, I'm going to say x average 70. X standard deviation was 10. Y average was 50. Y standard deviation was 12. Okay. And I want to say, okay, 90 on the midterm means 90, break up the standard units. So here is 90 minus 70 divided by 10. Right, so 90 is 2 standard deviations above the mean. So this is x in standard units. Take that and multiply by, take 2, multiply by r, right? So our correlation was, let's call it r. R was 0.75, so there it is. R times that. This is y in standard units. And then we convert back. So to convert back, we take 1.5 times the standard deviation of y, YSD, plus the y average to get back 68 on the final as predicted. I can just repeat this process. So I have here, I can do also 60 on the midterm. Let's do 60 on the midterm. That's not too bad. So here is 60. Just got to replace the 60 here. But this is 60 on the midterm is -1 in standard units. Convert that to y in standard units. There we go. Oops. R times -1. Prediction. Then take that, plug it back in. -1. And we predict that on the final, this unit would have gotten, oops, this is -0.75. Would have gotten a score of 41. Okay. Any questions about how we did that? This is something you should definitely know how to do. So if you don't get it now, I suggest you go back and take a look at the equations and make sure you kind of try out some examples and get all of that good. Get all of that in your head. Okay. So what we have here is, so I have here some functions. I just have here the functions that we defined yesterday. The first one converts an array of numbers to standard units. So here is like to convert stuff to standard units. Here's a correlation, so I can just compute a correlation. Okay, and what I want to do now is just go through some examples using these. Okay, so we saw before that we can do this whole calculation up here to make some predictions. Right? So we have a regression line. If we have the correlation coefficient and we know some stuff about x and y, we can use that to make predictions. But I don't want to type this whole thing over and over again. I just want to write a function so I can just make some predictions. So let's write that function. I want to first define the slope. So based on my previous slide, we know that the slope is r times the standard deviation of y over the standard deviation of x. Okay, so if I pass in a table with x and y columns, the slope is, so let me do that, turn the slope of the regression line. And just to be clear, this is original units. Okay. So to do that, I need to find the correlation, y, and then I can just return r times the standard deviation of x divided by standard deviation of y, standard deviation of the table's column y divided by standard deviation of the table's column x. This is my slope function. Now, if I want to find the intercept, it can be the same type of deal. There we go. Let's just copy and paste that. The intercept. And the way we do that is, let's take a look. So the average of y minus slope times the average of x. So I can just do the average of y, t dot column y. So this is the average of y minus slope times the average of x. And we just return that. So these are my two functions. One of them gives me the correlation, or these are my four functions. Standard units correlation. I have here a function that gives me the slope and the intercept of my line. So when I want to make predictions, I can just take that x value, multiply by the slope, add the intercept, and I have a prediction. So let's take a look at a data set. Oh, here they are. Oh, okay. Hopefully they both work. Compare. Okay, cool. They look the same. So I have here a table that is not defined. Let's not run that. Okay. I'm going to read in some data that we looked at on the very, very first day of lecture. If you recall, we were looking at the novel Little Women. And if you remember all the way back to the beginning of summer, we noticed that it looks like something's going on with the periods and characters, right? We saw that the more periods a chapter has, the more characters a chapter has, and vice versa. Let's show that. So here's Little Women. Let's scatter plot periods and characters. We see this. So for a novel, or for a chapter that had about 250 periods, it looks like we can expect about, I don't know, looks like 27,000 characters. When we get to like 400 periods, we look at 40,000 characters. Okay. So what we can do now is take a look at the correlation. So I have that function. So here's the correlation: Little Women, periods, and characters. We did as the correlation is pretty high, right? So 0.92 seems to suggest a pretty strong linear relationship. And what I can do now is I want to take these points and just show what I would predict given a regression line. So I know that I can draw a regression line. I'm going to write a function that'll make some predictions, and I'm going to plot those predictions here so we can see what a regression line would have predicted. Let's define that. So I have here def fit. This function will return the predicted y value for each x value. What I want to do is all I have to do now is take the slope, take the intercept, and return t slope times x values plus intercept, and that is it. Okay. So if I do that, I can take Little Women. I can call fit on Little Women, and I want to predict periods and characters. I can do 0 and 1 here. I have here a bunch of predictions. Let me put those back in my original table. Okay, so Little Women with column. Call that predictions. Let's call this fitted values. And let's do that. Bam. All right. So what do I see here? In my original novel, I had a chapter. Here's chapter 1. Chapter 1 had 189 periods. It had 21,000 characters. And if I fit a regression line, you notice that I would predict about the same, right? A little bit less than what it was originally, about 21,000 characters as well. let's take a look at that on the regression plot. So all I have to do now is take this and scatter plot. Scatter periods. And there we go. So what do we notice? We notice that the fitted values all fall on a line, which makes sense because we're doing linear regression. So we're saying, okay, I think all my points follow this line, generally speaking. So whenever I make a prediction, I'm going to predict something from this line. So blue is our original value. Yellow is what we predict. Here it all is. And you notice that the points are all pretty close because the correlation was pretty high. 0.9 is pretty high. Okay. Now, there's another way of looking at how the regression line comes about. So the first way of looking at the regression line is like to take the x and y values, multiply them together, and you get back correlation, and you get back the original regression line. Another way of looking at this regression line, just a different perspective on the same thing, that is also interesting if you look at it and extend it to other results. So we can look at the regression line as a line that minimizes the error. What do I mean by the error? So when I have this line here, here we go. So I have here some predictions, right? For every single predicted value of x, I'm not always going to get exactly the value of y. So for example, this point right here was kind of off the line. These points here are kind of close, so these look pretty good. This point down here looks pretty good. This one looks kind of off the line, right? And generally speaking, we think that the best line will go through most of the points. In mathematical terms, we think that the best line will try to minimize how far each point is from the line, right? So we could try to draw this line, we could try to draw that line, but we picked this line because this line seems like it goes through most of the points. The way we can quantify that is by looking at the error. So we define the error as the actual value minus the estimate. Okay, so if I have a prediction line, I have a point. The error there is how far a line was from the point. So we find the distance between the points, the y value, and the line's y value. That right there is our error. Usually some errors are positive and some are negative. So if the line goes through the middle of a cloud of points, you have some points that go above, which means a positive error. Some of the points that are below, negative error. So what we want to do to measure roughly how large the errors are is we square the errors to make them all positive, take the mean, take the square root. Sounds familiar because it's kind of like taking a standard deviation, right? And what we call this is the root mean squared error, RMSE. Sounds like some mathematical incantation, but I'll show you why it's useful in just a second. First, let's demo this. So I have here a little function that I'll just draw the same thing. And I want to demonstrate to you the idea of error. Okay, so let us take this function here, takes in the slope and an intercept and draws errors. So I'm going to save the slope. Oops. Let's call this LW reg slope, little women regression slope. Call slope on little women. And do the same thing for the intercept. Here's the intercept. Okay, if I pass in both the slope and the intercept, what this function will do is draw my line and also pick out some points and draw the error for these points. So we see here the line passes through. This little red bar is the error for this particular point. This red bar is the error for that point, that point, that point. Every single point, most of the points here have some error. And what we can do is we can try to draw some more lines, right? So let's try to draw. What if I didn't know the slope was supposed to be 87 and the intercept was supposed to be 4,000? What if I just do this? What if I thought the slope was 50 and the intercept was 10,000? What do we notice? One, the line doesn't really go through all of the points, and the error here is pretty big. So it looks like this point right here was closer than before, right? So if you look at this point, larger error, this one has a smaller error, but this point right here has a huge error. Okay. What about this one? So 50, let's try a negative 100, and we can start at 50,000. Okay. The sign looks pretty bad. It doesn't even go through most of the points, and indeed, the errors here, the length of these red lines is really long, right? Seems like a pretty bad line. And we can measure that with the error. So let's define the error. The root mean squared error is, first I want to draw that. So let's intercept just to draw, oops. And the way we calculate the error is we take the x values. So here we take little women dot column periods. Oh no. Don't bookmark all my tabs. That's a lot of tabs. I want this to go away. Y is equal to little women dot column characters. And the error is here. So what we can do is we can say, okay, take my prediction. So here are my fitted values. Take those fitted values, which is just slope times x plus intercept. Fit those values, find the error. So the error here is y minus my fitted values. Okay. Let me just do this outside the function so we can see what's going on. So I'm going to do that, put it outside the function. Here are my fitted values. Let's say my slope in this case was 50, and my intercept, let's take this example up above, which was 10,000. There we go. Some predictions, and I want to find out the error. So I can take my fitted values, just do y minus fitted, and that'll give me the error. Okay, so for every point, this is how far away the point is from my regression line. If I drew a regression line with slope 50 and intercept 10,000. So I want to take those, square them, take the square root, and that is the root mean squared error. Okay, and the way we do this is, so we square root, mean them, average them, and then take the square root of the average. Okay, this is the definition of the root mean squared error. I'm just going to put it back in my function so we can call it over and over again and see what we get. Okay, so put this back in. Put that back in. There we go. Oops. And I can just return this. All right. So let's take a look at the mean squared error for 50 and 10,000. So indeed, we find that the error here was the same as what we got before. It's about 4,000. 4,000. So that means that on average, I can expect a point to be about 4,000 away from the line. Right? So this one right here is like really far away. Maybe this is like 10,000. This one right here is pretty close, maybe like 1,000. It looks like on average, based on my root mean squared error, that most points are about 4,000 characters away. Okay. What about my other one, which is like the really diagonal one? So let's take negative 150,000. So lots of error, and indeed, the root mean squared error was 16,000, which was a lot more than before, 4,000. Right? So here's 16,000, here's 4,000. What if I try, let's try some more. What about this one? So here is 90. 90, let's try 4,000. Much smaller error. Looks like a much better line, right? And indeed, we see that the errors here are smaller, and the root mean squared error is only 2,000. So you can imagine, I see these points, I try out some lines. How do I decide which line is the best line? Well, I can find the error for every line. So let's say I drew this line at first. I was like, oh, it's bad. Let's try this line. Oh, it's even worse, right? I can fiddle around with the slope and intercept. And how do I decide which line is the best? I'll just pick the line that gives me the least error. That seems to be the best line. And it turns out that when you find the line that has the least error, you actually magically get back the regression line, this whole thing right here. It's magic. It's not magic, it's math. We won't go into why that happens. If you want to know more, you can take a linear algebra class. Okay? But it turns out that the regression line, so let me show that. And put that there. Let's put back in the original regression line slope, put in the original regression line intercept, and 2,700, a little bit less than even this line that looked pretty good. And indeed, if you try out a bunch of slopes and a bunch of intercepts, you will find that no choice of slope and intercept give you a better error than that. Magical. Kevin.
Is that why it's called least squares regression line? that where your name comes from?
Yeah, so this gives rise to a bunch of different names for the same thing, which is really unfortunate. You'll hear the regression line be called the least squares line, be called the best fit line, right? There's a bunch of different names for the same thing. And the basic idea is, well, the reason why the names come about is because there's multiple ways of looking at this line. The first way we saw was to compute that correlation thing and like use that to find the slope and the intercept. The other way, which I'm going to talk about today, is find a line that makes the error the least. So we call it the least squared error, the least squares line, because we're looking at the errors and we square the errors. Yeah. So I think Kevin is right. The least squares line, like terminology, comes from the fact that we're finding the squared error and finding the line that has the least squared error. Any other questions? All right. Well, so that least squares line, we're trying to find a line that gives me the least error. We define error as like this long root mean squared error thing. It just so happens that if you define error in that way, you'll get back the same regression line as you did before. Okay. If you minimize the root mean squared error, it's the same as minimizing just the mean squared error. So the only difference between this and this is I don't take the square root here, and I take the square root in this case. But either one is about the same, because as long as I find the line that gives me the least error, no matter between these two, I'm going to get the same line, because minimizing the regular error is the same as minimizing the square root of the error. So a bunch of names for the same thing: best fit line, least squares line, regression line. These all refer to the same thing, confusingly enough, but you'll see these being used interchangeably. All right, so let's take attendance. All right, and go for it. It puzzles me that there are no questions. Perhaps it's just too early on a Friday morning. But if you have any questions, now is a great time to ask while everyone's taking attendance and I'm waiting. Yeah, Andy?
Are the slides up?
Are the slides up? Let's check. Oh no, rejected. Okay. No wonder. Okay. And it should be up in about 2 minutes. Check. Sorry, thanks for that. Did you have a question, David?
So actually, I also wondering why we take the vertical rather than the
what a great question. So David's asking, okay, so, oh no, not my email. So why do we take the vertical distance instead of taking like this diagonal distance, which might be different? The truth is we just happen to choose the vertical distance. It's just a decision. You can choose to define your error in different ways. In this case, if you define your error by doing the vertical distance, you'll get back magically the same correlation line that we got before. It would be different. We can actually try it out, although it's a little bit complicated mathematically, because you have to look for the direction perpendicular to the line and like subtract away the distance there. So it's a little bit tricky. If you would like, you can try it out. I'll show you how to do something like that later on in this lecture. Kevin?
Is it true that we're taking the vertical distance because we're trying to predict the y value and compare that to the actual y values for a single x value?
Yeah. So one of the reasons why we take the vertical distance here is, as Kevin mentioned, we're trying to take given x, predict y, and we think that the best y value is, if I look at 200, I should probably predict the point in the middle of these points right here. That happens to be looking at the average y value, and because of that, that's related to why we've defined the error in this way. Another way of looking at this is, another thing to think about is if I flipped my x and y axes, right? So if I happen to look at the line, the best fit line between periods and characters, and try to predict periods based on characters, what I'll be doing there is it's a little bit hard to visualize. If you don't understand this, no problem. But for those of you who had questions about the flipping x and y thing and why the correlation and slope is the same, if I flip the x and y, you'll notice that instead of minimizing the vertical distance, I'm minimizing the horizontal distance. So I'm trying to say, given some characters, what do I think the period should be? That's minimizing the horizontal distance. So that's why I get slightly different lines. In fact, I think I can show you that. Let's try this out. I have not tested this beforehand. Who knows what will happen? So that, and let's try the slope the opposite way. Let's take the slope and do periods instead of characters. Predict periods based on characters. And oops, okay. Oh no, I have destroyed my function. How did I do that? Okay, scroll up, scroll up, scroll up, scroll up. Okay, to find that, scroll down, scroll down, scroll down. Here we go. Let's take that, take that. Unfortunately, I can't draw, oh darn, that looks bad. Unfortunately, I can't draw the, yeah, you have to draw this a different way. Okay, I tried to do something new, didn't work out. You have to draw like the x and you have to flip the x and y predictions as well. It becomes a little bit tricky to do that on the spot. But if you were to try to flip the x and y, you'll notice that that's equivalent to find a line that minimizes the horizontal error here. So whatever you're trying to predict, that axis is what error you're trying to minimize. In this case, we're trying to predict y values, so we minimize this error here. All right, so all of you are looking at me and you're like, why is this important? I didn't need this in the first place. I could have just done R, lived my life happily, made some predictions, I went on with my life. But the truth is that if you just look at it in the context of linear regression, this mean squared error thing is not super great. It doesn't seem super amazing because we already knew how to find that line. But that's, if you look at it, if you look at the line in this sense by minimizing the error, you can actually do a lot of other, you can also try out different errors and get back different lines, or maybe not lines. Let's see what happens. So here I have a function that defines the mean squared error. And what I'm going to do is I have this nifty function. So let's take this function, call it on, let's say I try a line of, let's say 90 and 4,000. Makes this big number. So what I'm doing here is instead of minimizing the squared error, I'm just minimizing the normal error. In fact, if I take the square root of this should look familiar, or maybe not. This is 2700, which is the same as this one. So here I'm just taking the error before the square root because because minimizing that is the same. So there's an error before the square root, error after the square root. Now, it turns out that I mentioned before that we can imagine picking the line as trying out some lines, right? We try out a bunch of different lines. We find the line that gives us the least error. And Python is really good at doing that. If you were to go ahead and try out by hand, that would take you ages, right? Pick a line and find like the lane, square all the lanes, and take the mean. It's a huge pain. But Python is really good at making a bunch of calculations at once. And so what we can do is tell Python, hey, find a line that minimizes the error for me, and just try out a bunch of numbers. Okay, so what I can do is, watch this. So if I define a function f of x, oops, and this function happens to be x minus 3 squared plus 1. So there's some function there on x. If I try out some values of f, so let's try f of 1. Let's try out f of 2, 3, 4, and 5. We'll see here that, okay, if I try this function on some values of x, it's 5, then it goes down, and it goes back up again. This is a pretty standard like parabola, what happens in a parabola, right? If you keep going, if you go, and the parabola goes lower and lower and lower, and then finally it doesn't go lower anymore, and then it starts going up. High, and then low, and then high. So we say, okay, the value of x that minimizes my function is 3, because I got the lowest error. And it turns out that I have this function in a data science package that will give me that. So if I call minimize and pass in a function, it will tell me what value will give me the lowest value of that. Which means if I call, so here I have this mean squared error function, 90 and 4,000, right? I want to minimize that squared error. So if I minimize that function, oh no, MSE. Look at these two numbers. Let me look at the MSE function again. I said here that this is a slope, this is an intercept, and all this function is doing, take the slope that I give it, take the intercept that I give it, and say, okay, if I had a line that had this slope and this intercept, how much error would I get when I try to fit the line? Okay. And indeed, if I try out some different slopes and different intercepts, I'll get different errors, as I mentioned before. And I told Python, find the best slope, find the best intercept that gives me the least error. These look familiar because if I look at the original regression, let's say slope, the original regression intercept, vicious. They're exactly the same. So two ways of getting the same thing. But now let me show you something interesting, which is with this little minimize idea, I can do nonlinear regression. Okay, so watch this. So here I have shot put data. This right here is basically some athletes who lifted weights. I believe this is like the one rep max like power clean lift, which involves some crazy manipulation of joints to lift weights. But this is the weight they lifted, and this is how far they can throw a shot put. If you're not familiar with a shot put, it's like this metal ball, and people try to see how far they can throw it. Okay, so farther the better. It's just a measure of athleticism. And what we're trying to do here is, let's scatter plot that. We say, okay, if I look at this, the weight lifted in that exercise, I want to predict how far I can throw that shot put. If you look at this data, it looks like it doesn't really follow a line. Like we have this kind of L-shaped looking thing as we've seen before. So here's kind of like upward sloping, and here's like some other upward sloping. And indeed, if I were to fit a line to this, so if I just add fit line equals true, you can draw a line without having to do any of that mathematical finagling that we did before, but it doesn't give you the slope and the intercept. It just draws a line. So here's a line. It looks like it does go through most of the points, but like the points down here are kind of left out. Okay. And what we can do now is we can say, okay, it looks like there's a curve in my data. Can I fit a curve instead of a line? And it turns out that now we can. So watch this. I'm going to take my MSE. I'm going to call this shot put. Shot put, and let's try to fit a quadratic function. So before we had a linear function, which looked like this, ax plus b. This is what we tried to fit before. We tried to tweak a and tweak b so that I got the line that minimizes the squared error. I could instead try to find the best quadratic curve. It looks like this, ax squared plus bx plus c. And I can tell Python, okay, try to figure out, tweak with the values of a, b, and c in order to find the best curve that fits my data. If that curve happens to minimize the squared error, I'm going to call it the best. Let's try to see what happens. So let's call this quad MSE. Here is A, here's B, here's C. And the way we do this is when I fit my data, I'm going to do A times x squared plus B times x plus C. And that's all I need to change. Okay? So we're going to try this out. If I try to fit the line, if I try to fit the curve maybe like 1x squared plus x plus 1, I get some mean squared error. This is really, really high. But maybe we can tell Python to minimize this for me. Minimize that. We get here some numbers. But what I can do now is I can plot them so we can kind of get a sense of what this is doing. Okay, so let's take this column, x, column 0. So take my x values, and I'm going to predict. Take that. And instead of A, I'm going to call this, so A is shot put. Let's call this best. Best, I'm going to save this value. A little nifty trick is if you have 3 values in an array like this, I can try to do this. A, B, and C equals best. And what Python will do is it'll actually like assign all three values at once, which is really nifty. Okay, assign all three values at once. Actually, let me do that there so you can see it. Let's see. Okay, so here I'm doing the same thing. A times x squared plus bx plus c. Here are my predictions for each value of x. Let's plot them. So I'm going to take my shot put table, add in the column width, column best quadratic, and pass in this guy right here. Let's call this quad fitted. Just leave that there so we can see what it is. Quad fitted. There's my predictions. And oh no, it seems to be quite off. What did I do wrong?
In your function, women columns.
You're right. Shot put. Thank you. Thank you. Okay. Shot put. Let's try this again. There we go. There we go. There we go. Okay, that seems a lot more reasonable. Thank you, Andy. All right, now let's scatter plot this. Scatter plot the weight lifted, and what do you know? We get here a curve. We get here a curve. Okay. So the reason why the idea of like minimizing and all that stuff is useful to us is this idea right here. All I did here was, okay, minus the shot put thing. All I did here was change how I fit in my values. I can tell Python find the best set of A, B, and C that give me like the best curve or the best line or anything else that I want. Python was able to do that. So with this, you can do nonlinear regression, you can do quadratic regression, you can do like exponential regression. You can basically do whatever you want just by changing what goes in here. And with this cool little idea, not only can you do, this is actually the basis of a lot of machine learning techniques. A lot of machine learning techniques have like complicated functions that calculate error. But as long as we can get the function looking correct, we can just throw it at a computer and say, go ahead and minimize this. The computer will go ahead and try out a bunch of different values and say, okay, these are the points that best fit your data. And that's how you can make predictions. Any questions? Yes, Alan?
So how do we decide what kind of like regression line or regression curve we want to use?
Oh, what a good question. So how do we decide whether a line is best or a curve, or like a quadratic curve is best, or like x cubed is best? We'll go into a little bit later on today, but in truth, like that's a topic for another class, probably a machine learning class. Maybe Data 100 if you plan to take it. All right. So just to recap, let me turn this off. Any objections? All right, it's off. So, oh, that wasn't supposed to show up all at once, but here we go. Basically, this wall of text is saying, we can tell Python to minimize some function. And in this case, if we minimize the error function, we get back the best fit line for the mean squared error. If we happen to change our fitted, the way our error is calculating, we can fit other things as well. We can fit curves and more complicated things. Okay. So here we had a function MSE that had a slope and an intercept, and we said, okay, this will give me the error if these two things combine to form a line. I can call minimize on my function to get back the best slope and the best intercept. In conclusion, we have a regression line that lets us make predictions. We have two ways of computing, right? Find R with the multiplying x and y, or just find the slope and intercept directly by using like the minimize thing. In particular, if we minimize nonlinear functions, we have nonlinear regression. So here, just to start off the break, end lecture, and the first half of the lecture, I have here data IRL. This data is showing a probability of death by country. It looks like in every country, you have a 100% chance of dying. So why is this not useful? It's not useful because it doesn't show me any information about any country. Okay, let's try another one. Here's another one. So here I have chemical elements on the left-hand side, US states on the right-hand side. It turns out that there are some chemical elements that also happen to be abbreviations of US states. Why is this useful? It's not useful. It's data in real life. All right, take a break.
why should the last two elements on the chemical element not have names? So maybe there's some